University of Illinois. We'll be speaking about Vesto Slipher and the development of nebular spectrographs.
Well, I'm used to talking to large classes, and I prefer not to use a microphone, but you raise your hand if you can't hear me. Yesterday, we all heard an excellent talk by Robert Smith that was entitled V.M. Slipher, Master of the Spectrograph. And my talk could have been entitled exactly the same, but it's rather interesting that the content of mine is almost 90 degrees out of phase with what he talked about. I will talk about some historical topics, but those of you who are historians, feel free to give your input and comment on those. I do it from the perspective of an astronomer, and in particular, my talk, as you'll see, is directed toward the technical aspects of building spectrographs. I'm currently in the process of building for myself a nebular spectrograph, and that's essentially what Vesto Slipher did, and he was the one who actually derived or wrote down the fundamental equations that allow you to do that design, and that by itself is just very remarkable that he would do that. So first, an outline of what I'm going to say, and that is a technical discussion of exactly what Vesto Slipher did to make his detections. And before I go through these 4 items, I will tell you that you should keep your ears open throughout the talk for the F ratio of the camera lens. That's the key parameter to make a nebular spectrograph, especially in the era of Vesto Slipher, work well. And for those of you who don't think about F ratios, I'll just tell you that you take the focal length of a lens. Here's the lens. You take the focal length and you divide it by the diameter of the lens. And in this era of the early 1900s, it was very easy to build, to make lenses that were f15, f13, f10. The minute you get to f1, which is the ideal way that nebular spectrographs work, it's hard optically to get good images. And the initial spectrographs that were built historically, I'll give the names here of Bunsen and Kirchhoff, were all long focal length lenses because they gave good images. So what I'll do is go through the highlights of early spectroscopy, both stellar spectroscopy very quickly, and then nebular spectroscopy. And as I hinted at yesterday, I'll tell you about this gentleman, Edward Fath, who historically was related, he comes from Lowell Observatory, and so those comments that Robert Smith made yesterday about the competition between Lowell Observatory and Lick Observatory and the director of Lick Observatory, Campbell, play into the presentation here. I'll eventually get to a slide that shows the optical parameters that it takes to make a good spectrograph. As I said, Vesto Slipher deduced those, figured those out. And then almost key to the whole presentation is what did Vesto Slipher really do that allowed him to measure those Doppler shifts? What did he do better? And the list is a long one, putting him far above his competition. And then I'll tell you from a technical point of view, how is it that Humason and Hubble, that team, pushed to fainter magnitude, fainter galaxies in the velocity distance relationship, and it's directly related to the F ratio of that camera lens. I said early on people started out at f15, Slipher and Fath even used lenses around f3, and then Humason eventually used a lens that was f.59. And these are points that people, like if you don't build instruments, you would just sort of not be aware of that. Initially, spectroscopy was done in the lab on sparks, on flames. Then people moved to the solar spectrum and eventually to stars. And the names associated with that are Bunsen, you can see it here, Kirchhoff, I have the first names of these other people, Angelo Secchi, Anders Angstrom, Hermann Vogel, Louis Rutherford, to be distinguished from the very famous Rutherford. This is an observer who was in the state of New York, and especially William Huggins in England. And all of these spectra of sparks, the sun, and stars required very simple optics. People use things that you might consider off the shelf, long focal length lenses. And the only nebulae that were actually resolved spectroscopically in that early era were planetary nebulae, because they also have a high surface brightness. They give out their light at a specific wavelength, and when you're looking at it with a spectroscope, visually you can see that wavelength. Now, you can see those specific emission lines. Now, those early workers who used those long focal length spectrographs saw the spectra of what was called spirals at the time. Of course, it was elliptical and spiral galaxies, and they called them continuous because they could not resolve the subtle absorption lines that were made by the constituent stars. And in order to see those, you have to move to a spectrograph camera that has an f3 or an f2 focal length. And then, of course, to measure the Doppler shift, you have to record the spectrum in a way with a comparison spectrum. Actually, William Huggins tried to measure Doppler shifts of stars visually and was unsuccessful at doing that. And so the advances in nebular spectroscopy are directly tied to the advances in the technology for the photographic process. And initially, what was called the wet collodion process was used in the 1860s, and Huggins tried that process. You have to keep the emulsion wet during the exposure and then immediately develop it. But progress was made in astronomy only after 1875, when the conventional emulsions that were called gelatin dry plate process were introduced. Now, before I say that, I'll remind you that from Robert Smith's presentation, when Slipher first came to Lowell Observatory, he was given the brochure spectrograph. He was given the task of measuring the rotation velocities of planets. He started out testing the spectrograph by looking for the spectrum of Jupiter, and then moving on to Saturn and Venus. And all of those are high surface brightness objects. He was able to see them immediately, test the spectrograph, and do everything. For example, Venus, I looked this up before giving this talk here, has an apparent magnitude surface brightness of, it varies between 1.5 and 4 magnitudes per square arc second. And for astronomers, that's huge. It's brighter than the brightness of the daytime sky. The nuclei of galaxies that Slipher eventually detected have a surface brightness of 10 to 12 magnitudes per square arc second. That's 8 magnitudes difference. And if you want to detect a disk spectroscopically, to detect the disk of a spiral galaxy, which was not in the range of what Vesto Slipher did, you have to go down to 21 magnitudes per square arc second. That's another 10 magnitudes down, well beyond what was available even to Slipher. Now, it's interesting to say that William Huggins, who essentially ended his work with a publication, as I understand it, in 1899, reports in that publication that he had detected the spectrum of the Andromeda galaxy. He did it on a photographic plate, and he reported that there were absorption lines in the spectrum, but in his compilation of his work, published in 1899, he sort of denied that really was what he saw. In all these cases, comparison spectra were put along with the object spectrum on the same plate, and he worried that the spectrum of the sun had contaminated his spectrum of Andromeda. He was apparently using the moon as a comparison source. And if I don't say so, Vesto Slipher used the spectrograph, even modified for the nebulae. He used as a comparison source the planet Saturn. He would observe a nebula, then he would look at Saturn for his comparison source. And in the case of Huggins, he did that with the moon and was afraid he had contaminated the image, and so he sort of denied that there was an absorption line spectrum of Andromeda. He was, throughout his life, sort of prejudiced in favor of emission line spectra as an explanation for what nebulae were. He was the one who discovered the planetary nebula have emission line spectra, and he thought that all of them may have emission line spectrum. The first sort of credible detection of the Andromeda galaxy absorption line spectra is usually ascribed to Julius Scheiner in 1899, but there was a second opinion about that spectrum given by Vogel, who was at the same observatory. He was I won't go back a slide, but he was a stellar spectroscopist who saw the plate of Scheiner and said, well, the signal to noise isn't high enough for me personally, as Vogel said, to say that the Andromeda Nebula really was an absorption line system. Now, you notice the date here, 1899, long after the dry emulsion process was available, and the next person to contribute is this fellow Edward Fath, who, along with Slipher, gets sort of an abbreviated part of history. I'll just go ahead with the presentation here. All of these astronomers detected the spectra of spirals and saw absorption lines. So when Slipher arrived at the point of doing his observations, he concentrated not on the nature of the spectrum, whether it was emission line or absorption line. People accepted that it was an absorption line spectrum, and that allowed Slipher to concentrate on measuring the Doppler shift. But Fath was the most important contributor, or you might say competitor, at that time. He tested camera lenses when he was a student at Lowell Observatory for his PhD thesis. He tried at one point an F3 lens and was able to see the absorption line spectra of spirals. He then switched to an F2 lens for his work. And by the time Slipher had detected the M31 spectrum, the 100-year anniversary that we're celebrating now, Fath had not only detected the absorption line spectrum in Andromeda, but he had 10 other spiral galaxies that he had detected, a list of maybe 8 globular clusters that he had detected the spectra of. And he by just about the time Slipher got his spectrum of Andromeda, Fath had already published 3 papers in the Astrophysical Journal describing those spectra. It didn't resolve the issue as to what they're constituent, what they're made of, because in Fath observations, one of the 10 galaxies that he observed was NGC 1068, which is a Seyfert galaxy and has all kinds of emission lines. And he saw the composite spectrum of an absorption line spectrum, which he had seen in the other spiral galaxies, with these emission lines. and it's somewhat confused the situation. There also is the issue that was brought up yesterday about whether Fath had detected the radial velocity of a globular cluster. And the story that people tell is that it was too high for him to believe, and therefore he dismissed it. But the real story is this, that Fath built his spectrograph for his PhD thesis at Lick Observatory out of a wooden box. It wasn't even metal. And furthermore, when he, as I understand it from reading the original papers, when he went to make his comparison spectra, he took the spectrograph off the telescope and sat it in front of a lamp. And if you're going to measure a radial velocity standard, you just cannot do that. And he was correct to say that he would not trust the radial velocity of his globular cluster because the techniques were just extremely poor. Here's a picture of Edward Fath. He was a PhD student at Lick Observatory. He moved from there to Mount Wilson Observatory and worked on the 60-inch telescope for 3 years, and eventually moved to Wisconsin to be the head of a small observatory. In the acknowledgments to the paper he published on his PhD thesis, this is what he says here. He says, he acknowledges the support of Director Campbell for resources and helpful interest in the work. And to repeat what Robert Smith said yesterday, Campbell stated clearly that the radial velocities of these nebulae was a very high priority item. And yet he had this gentleman, Edward Fath, as a student who was just not up to the task of measuring any radial velocities. It's quite a feat for him to detect the absorption line spectra, to see Seyfert galaxy emission line spectra and so on, but there was no way that he was going to measure those Doppler shifts. And here's a list of the galaxies that he, where his spectra are published in the Astrophysical Journal, not only Andromeda, but all of these, and he discusses them in detail in his papers. Now, here's sort of the historical part, contribution that I'll make here. The key historical part. The fact is that Percival Lowell encouraged Vesto Slipher to measure the spectra of spiral nebulae in 1906, and he proceeded to complete other projects and not direct himself wholeheartedly toward this effort. And he started to devote more attention to it in about 1910. Now, what others may not have realized before is that there was a conference held at Mount Wilson Observatory to somewhat commemorate the opening of the 60-inch reflecting telescope in August 29th to September 3rd of 1910. And this was a very large conference. On my computer here I have a group picture of the 80 people who were there, very famous astronomers, and the Carnegie Observatory even funded their travel from Europe to attract people to come to this conference. And Vesto Slipher went there, and he went there at a time when Fath had moved from Lick Observatory to Mount Wilson for his 3 years of work. And here's a picture of Vesto Slipher at that conference with, this is Carl Schwarzschild, here's Cap Time, and other people in the background. And it turns out that if you look in the archives, this is on the next slide, of the correspondence here at Lowell Observatory, you see that immediately after this conference was over, Fath and Slipher began to correspond with each other, and there are a set of 10 letters that detail exactly what they talked about. And it looked somewhat, to me, when I read these, I must say that they were provided in a very rapid and kind way by the librarian here at Lowell Observatory, Lauren Edmondson. And when I went through those letters, it seemed like there was some kind of a cat and mouse game going on between these two gentlemen as to exactly what was going to be revealed. And what Slipher wanted to know most keenly, it seemed to me, was whether a nebular spectrograph on the Crosley 36-inch telescope at Lick had a speed that was any different than a nebular spectrograph on the 60-inch telescope at Mount Wilson. That's a big difference in aperture, and Slipher had deduced, very interestingly, that if you have a true nebular spectrograph, the speed of the spectrograph, that is the energy concentration at the plate that you see to detect the nebula, should not change as a function of aperture of the telescope or the F ratio of the telescope, that it should depend only on the F ratio of the camera lens. And he wanted to know, Fath could answer that question because he had worked at both telescopes. And it seemed Fath's answer was that, well, the spectrographs were different. He couldn't really tell. And it's not clear to me whether he was sort of obscuring the facts or whether it was a true answer. And eventually, in these 10 letters, eventually Slipher just comes out and says what the relationship is. He just tells Fath what the relationship is in about 1911. And Fath continued his work, his observing through 1911, and he, in a sense, took advantage of the knowledge or the thought process that Vesto Slipher was going through, and those statements were in a letter on February 18th, 1911, that the telescope diameter, the telescope F ratio do not matter. It's just the focal ratio of the spectrograph camera that increases what is called the speed of the spectrograph. That is the energy concentration at the detector when you do the exposure. And because these were photographic exposures, that was sort of the key parameter to getting a good plate of these spectra.
So then how did Fath take advantage? How did he take advantage from this?
Well, I don't know that he did.
Okay.
I don't know that he did. And I think there was sort of a crossover there, between sort of an equal gain by both of those gentlemen. The fact is, it may have been in conversations at that meeting that Vesto Slipher learned that a fast camera lens would work to your advantage. But Fath never wrote down in a verbal, I would call it algebraic way. You read Slipher's papers and he says what those dependencies are. He does it in a verbal way. He doesn't write the equation down, he says it in a verbal way. Nothing in Fath's publications mention anything about this, just that he had tried it, that he did it. He worked first with an F3 lens, camera lens, and then an F2 lens. Now, these are Slipher's statements. It's not only that the telescope aperture and F ratio don't matter all that much. They do matter, and I could explain it to any astronomer who wants to know in a modern context what that means. But in the context of Slipher's detection, they don't matter that much. The spectral dispersion doesn't matter as long as the spectrograph slit is adjusted properly to see the right contrast of the absorption lines. The wider you open the slit, the less the contrast can go down. But the wider you open it, the more flux you get. And Slipher worked in his 41 spectra, whatever he measured, he worked with a slit that was 8.25 arc seconds wide, extremely wide on modern scale. And then the camera F ratio increases the signal level above the threshold of detection. And in this photographic era, those people who are old enough like me to remember the techniques of astronomical photography, there's a toe of the curve in detecting in the photographic process, and you have to get the flux high enough to get onto the linear part of the curve. That's what people used to say. Now, here, this is sort of the key to why Vesto Slipher succeeded. He was a very careful experimentalist. The key, he had a degree from Indiana in mechanical engineering, and I think it would only be someone with that background who could drive to the answer. Fath had none of this knowledge, no way. The first thing Slipher did was temperature stabilize his spectrograph. That's exactly what people do in exoplanet work these days to get to meter per second accuracy. You temperature stabilize your spectrograph. The spectrograph sits out in the dome, and as the night goes along, the temperature drops, and the size of the spectrograph changes, and the position of the spectral lines and the focal plane shift. As mentioned by Robert Smith yesterday, early on, after getting the brochure spectrograph, Vesto Slipher was right in there doing radial velocity standard stars on the initial configuration of the brochure spectrograph. No testing whether he could actually measure a given radial velocity. He sensitized his own photographic emulsions, and for his planetary work, used dyes to extend the spectral response of the photographic emulsions. He applied lab reference arc spectra through the telescope using Leyden jar capacitors to give the arc spectrum, and then he repeated his detections over and over to make sure he was on the right track. And it was in 1952 that Ira Bowen wrote down in a paper in an algebraic form for sort of modern instrument designers the three conditions that students learn in astronomy about how to design spectrographs. In one case, you have a spectrograph with a slit wide enough that all the light goes down through the slit. And in that case, the sensitivity of the spectrograph, or you might call the speed, the energy concentration at the detector, goes up as the diameter squared of the telescope. If you have a spectrograph where the slit is narrow enough relative to the seeing disk of the telescope, you don't win that much. The speed goes up by the diameter of the main telescope aperture. And when you do true nebular spectroscopy, the diameter drops out completely. Now, nothing is truly nebular, a nebular spectrograph, because these galaxies have a nucleus and they have an energy concentration. You have to keep that in mind. But for the sake of Fath and Slipher, these were like nebular spectrographs. And in that sense, the speed is the surface brightness of the object, which I told you, like for Venus, it's huge, and for the nuclei of the galaxies, given the photographic emulsions, it's just detectable. And then you take the slit width times the dispersion. That's essentially to take out of this surface brightness, which is given per unit wavelength, to take out the wavelength portion of it. And then you divide by the spectrograph camera focal length squared. And then that's how you get the speed. That's how you get the energy concentration at the plate high enough to make this.
So do you think Slipher did derive it algebraically, but didn't write it down?
Exactly. And when you read it in these letters that he sent to Fath, you can see it just very transparent. And you can even see it in his papers. You know, I did exactly what you did for his papers, and I just read what was in there, and it's all in very terse language. Very clearly stated, very clearly stated. This is his Slipher's best spectrum of Andromeda, and you can see these absorption lines here. And I'm not quite sure what these lines are here. This is probably, it may be Saturn, but or it may be the emission line.
Is that called the arc?
The arc. Well, I know it's either the arc or the. Yeah, I guess it is. Now here's a summary of those camera focal lengths. You see now that it goes as one of the focal lengths squared for the detection of nebulae. Fath started with an f3 camera lens, and by 1911 he had switched to f2. Slipher started with the brochure spectrograph as delivered by brochure at f14.2. You see it was a standard stellar spectrograph at that point, and he rebuilt it to have what he called the commercial Wattlander f2.5 lens for all the spectra that he took. Now Humason, much later, started out at f1.43, and there's no question that the Mount Wilson people had read these papers by Slipher, and they knew exactly what to do. But it turns out that this camera lens here didn't have a good enough focus to give spectra that you could measure. And so most of the spectra that were taken initially were abandoned or retaken in favor of a lens that was built at Mount Wilson, or I call Mount Palomar, that had this amazing F ratio. And it was because of this that Humason was able to push much fainter, very quickly, push much fainter. And that's in optics, or in astronomical optics, that's a very famous lens. It's called a Rayton camera lens. It was made by the Rayton company. It's an enlarged, hugely enlarged model of a 4mm microscope objective. And optical design in that day was very difficult. It was done by hand. These days there are programs that optimize optical design. It's almost like a solid glass camera. The focal point is back here, nearly in contact with the glass. And then I just sort of, after this presentation, it's essentially over, I'll just show you some pictures. This is the modified version of the prism and camera lens section that Vesto Slipher used. It's in the museum at Lowell Observatory. The plate goes here, the camera lens here, and as I said, it's f1.5. This bolts onto the brochure spectrograph, so the collimating lens is not here, it's on the brochure spectrograph. This is the measuring engine that Slipher used. The way they did it in that day, the more modern astronomers will be interested in this. They took spectra, standard sources, stars, giant stars that had spectra similar to the galaxies, and then they cross-correlated them visually. That is, they lined them up visually and used all the information in all the absorption lines, even though some of them are faint. And when they saw a correspondence between the two, that was sort of the fiducial point for making the measurement of the Doppler shift. And then from that, they measured the position of the comparison lines on the two spectra to get the redshift. So of course, it uses all the information and gives an accurate result. And now, maybe I'll show this next slide here. I sort of got into this not only because I'm designing or building a spectrograph myself, but I worked for a long time at Mount Wilson Observatory, where I have an adaptive optics system, and in the basement of the Mount Wilson Observatory are all the old instruments, and they look sort of like a junk heap. And amongst that are the spectrograph parts that Humason actually used in 1928 through 1931, and with the help of other people there at the observatory, I actually found those parts. You couldn't identify them immediately. And this shows the collimating lens, the prism section, and the place where the f.59 lens went for Humason's spectrograph. And then the plate holder goes right here. And then this is the picture of the plate holder. The plates were very small. The spectra were all very small. The spectrum of Andromeda is no more than a few millimeters long to concentrate the energy. And then this last shot here shows how the spectrograph at Mount Wilson was mounted on the telescope. The light from the telescope comes through here, goes through the collimator, and then that trombone-looking item I showed you just a minute ago is right here, and the light comes up and up to the plate. So that's the end of the presentation.
I think we have time for one quick question. We can do a quick question, John.
Quick comment. You mentioned Lewis Rutherford. Poor Rutherford, I think he is one of the people who most frequently has his name misspelled in the history of astronomy. And so the spelling of his name is not like the famous physicist, but it's printed that way in a zillion places, and I just call that to folks' attention that there are two U's, not just one.
Good. No change.
Okay, is that clear? One more time, please.